Welcome to the second lecture of the Marketing and Customer Support module. The topic of this lecture is Ethical Design Framework. To understand the content of this lecture, we recommend that you have previously watched the lectures of Module 1, Introduction to Blockchain Methodology, and Module 3, Fundamentals of Blockchain and Distributed Ledger Technology. The agenda. This lecture is all about the ethical value of blockchain and how to communicate it. We start with an overview of the learning objectives. Then we talk about the overall value of blockchain and the social impact potential of blockchain. Afterwards, we will introduce the ethical design framework and close the lecture with a conclusion. This slide shows an overview of the knowledge, skills, responsibilities, and autonomies you will acquire in this lecture. In marketing, the communication of added value is of particular importance. Blockchain technology has many supporters, but also just as many skeptics. Therefore, it is important to be able to communicate the ethical added value, but also the dangers of technology. After this lecture, you should have an awareness of customer success design. You should be able to create awareness of blockchain use among a broader audience and have the capability to critically analyze and ethically evaluate marketing strategies. This lecture outlines why intentionality of design, which is important with any technology, is particularly crucial with blockchain. We all know that technology is not neutral. We see that every day in the algorithms embedded in social media or the search engines, but also in technologies like AI. Value and biases are embedded in the code. How the problem is defined and by whom, who is building the solution, how it gets programmed and implemented, who has access, and what rules are created have consequences in intentional and unintentional ways. In the application and implementation of blockchain, it is critical to understand that seemingly innocuous design choices have surrounding ethical implications on people's lives. This lecture is based on the Blockchain Ethical Design Framework by Cara Lapointe and Lara Fishbane. For further information and access to the document, please see the references at the end of this presentation. The key attributes of blockchain. To begin with, let's take a closer look at the key attributes of blockchain technology. The unique combination of attributes, transparency, trust, and immutability of transactions makes blockchain technology appealing in its application for social impact. Blockchain has a spectrum of key attributes that are highly interdependent and which vary in their relative dominance based on design and implementation. All of these key attributes should be considered as potential attributes since their exact realization depends on the detailed design of a particular blockchain system. Decisions about how to optimize combinations of these attributes in a blockchain will determine the impact of its application and create potentially significant consequences on people's lives. Number 1, trust. Strict governance rules, cryptography, and immutability of transactions work together to provide strong security for individuals interacting directly on a distributed network without a central trusted authority. Number 2, immutability. Immutable transactions recorded on a blockchain cannot be changed or removed. To change a transaction on the blockchain, a new transaction needs to be added to reverse the effects of the original. In immutable ledgers, there is no way to erase the record of a transaction. Number 3, pseudonymity. Having a public and private key systems, participants have a public-facing digital address that is not publicly associated to them, but over which they exercise unique control. This provides pseudonymity through encryption that creates the possibility of effective anonymity for participants. Number 4, verifiability. Transactions on a blockchain are immediately auditable in real time. As an immutable sequence digital ledger, a blockchain allows the complete record of transactions to be directly verified. Number 5, controllability. The tracking of individual assets uniquely on a blockchain allows an individual to exercise effective and exclusive control over data or digital assets. Furthermore, transactions on a blockchain allow the secure transfer of control between individuals over the network. Number 6, security. The use of encryption algorithms combined with the disaggregation of data across a distributed network of nodes, i.e., computers, provides security against attempts to destroy or change the record of transactions. Number 7, disintermediation. Using direct transactions, blockchain technology can streamline processes by cutting out unnecessary intermediaries and processes, as well as reduce the risk of errors that usually come with extra transactions in a system. And number 8, transparency. Identical copies of the entire record of transactions are available to all participants at all times. This is often referred to as a distributed ledger. In some cases, these ledgers are publicly available to anyone. The ledger provides transparency of transactions to anyone with access. These key attributes are anchored differently depending on the blockchain design. You can't talk about the blockchain. There are countless design and implementation options that create functionally different blockchain systems. One of the most important distinctions between blockchains is between permissionless and permissioned systems. In permissionless versions, anyone can participate in the creation of the blocks for a blockchain. In permissioned applications, only authorized entities can do so. Similarly, some blockchain ledgers are publicly viewable, while others can only be viewed by a specific group of people. Furthermore, there are both open source blockchain platforms and proprietary or customized options for blockchain development. These are just some of the many options that give blockchain its flexibility and extensibility. Depending on how it is designed and implemented, blockchains can have a wide range of consequences for people. Decision paths for the different types of blockchain can be found in Module 4, Blockchain Business Management and Planning. Social impact potential of blockchain. The potential transformative power of blockchain is enormous, but much of this transformation will be achieved through the spread of practical applications of the technology. The possibilities of blockchain are already being explored in a wide range of social impact initiatives, organizations, and applications. Following are some categories where blockchain has shown promise. Social impact use cases. Digital identity. One of the most important things that blockchain can do is create a digital identity. The mutability and verifiability of blockchain systems enables the establishment of permanent and portable digital identities. These identities are linked to a unique individual and can be used in a variety of contexts to prove identity or credentials. This capability provides extensive social good benefits. One example is the effort to supply digital identities to people living without officially recognized identities in order to provide those individuals with economic, political, and social opportunity. Another example is a recently launched blockchain in New York City by the organization Blockchain for Change that creates a digital identity system to connect homeless individuals with efficient access to services and programs. Asset tracking. Blockchain has significant potential for supply chain management and tracking assets. For example, IBM is working with several big food retailers to prevent fraud by verifiably tracking the provenance of food and to increase food safety by efficiently facilitating rapid responses to recalls of contaminated food. Blockchain technology can also help governments, aid agencies, and individual donors to transparently track financial resources, such as humanitarian or disaster assistance funds, from the point of origin to the point of application. Enterprise efficiency. Blockchain offers tremendous potential for its ability to aggregate, verify, and transact with multiple data sources. Many governments and businesses are considering applying blockchains to manage internal transactions. A recent report from Accenture says blockchain's transformational potential lies in its power to create efficient data sharing and reconciliation processes within an enterprise. Blockchain has great potential for creating outcomes through smart contracts, in which computers automatically execute an action once conditions are met. These contracts increase the speed and accountability of managing transactions. Outcome-based contracts do not have to be executed on a blockchain, but putting them on an immutable blockchain provides irreversible security guarantees that make it harder for users to violate the contracts. Expanding access to services. Blockchain can increase inclusivity by allowing people who do not have formal identity credentials or credit histories to build a secure digital identity, thus reducing risks for lenders. For example, it can aggregate personal identifiers such as financial transaction histories, property records, trust networks, and education records so that people can develop a portable and vetted personal history that gives them access to formal services. Protecting vital records. Governments and other entities across the globe are exploring blockchain applications for vital record protection. Estonia is one of the world's leading governments in the adoption of e-government technologies for creating digital registries and online government services, which include securing over 1 million public health records with a form of blockchain technology. The records themselves are kept in a traditional database, and to enhance the security of private information, the blockchain logs every time those records are accessed or altered. In addition to providing auditable records, blockchain protects records by scattering data through a distributed blockchain ledger, thus reducing vulnerabilities compared with data that is aggregated and stored in one location. Recording public transactions. Blockchain-based land registries are being piloted in countries around the world so it can be used to record property titles and transfers. Enabling secure mobile voting. Blockchain-based technologies are being explored to provide secure mobile voting. Some institutions are leveraging the attributes of blockchain to provide end-to-end verifiable voting on an accessible platform that reduces the barriers to voting. Preventing human trafficking. Governments and organizations are looking at the promise of blockchains to combat and prevent human trafficking. The United Nations have partnered with the World Identity Network to launch a pilot project in Moldova of a blockchain-based digital identity system for undocumented children. The U.S. Department of State is also working with Coca-Cola and other private partners to create blockchain-based secure registries for workers to help prevent forced labor worldwide. Improving medical research and healthcare. Blockchains are being piloted to improve medical research and healthcare. A prototype for electronic health records and medical research data called MedRec was developed through a collaboration between the Massachusetts Institute of Technology Media Lab and the Beth Israel Deaconess Medical Center. Using MedRec, control and responsibility over medical records are shifted from institutions back to the patients, who are ultimately in control of where those records can travel. What makes blockchain so relevant is also its greatest challenge, the interdependence of its attributes. It is impossible to focus solely on one desired feature without understanding and accounting for the interaction of all the attributes of blockchain. In the design process, to optimize the desired attributes of blockchain for a given application, there will always be trade-offs, which will result in functionally different blockchain systems. Small design choices can have resounding ethical consequences for people and communities. Here is a short overview of some of the blockchain design consequences. Codifying negative social impacts. One possible consequence for end users of blockchain technology is the codification and intensification of existing negative social dynamics. Blockchain could be used as a tool to further consolidate control over individuals or entities, or to create secret agreements to circumvent laws and regulations. For example, a blockchain that provides access to financial services through verification based on members of a community collectively checking a person's creditworthiness has very different implications for the end users than a blockchain based on a person's financial transaction history, property ownership, and educational background. The first example risks codifying community biases, while the second risks codifying the status quo. Without intentional design, blockchain could risk exacerbating inequalities. The risks of transparent or immutable personal information. Transparency of personally identifiable information could put someone at risk of exploitation, while transparency of ethnic or religious background, sexual orientation, or other identifiers could put a person at risk of persecution. Immutability of information on a blockchain removes the ability to be forgotten. Should a political refugee, witness to a crime, or survivor of domestic abuse have the right to anonymity or to create a new identity? Even if someone legally changed her name, she would be unable to disassociate her biometrics from the old digital identity in the blockchain. Is there a minimally viable set of identifiers that should be used to create a digital identity in order to help mitigate these effects? For example, if the purpose of a blockchain is to enable short-term access to services or resources, such as a post-disaster assistance, is it even necessary to include any personally identifiable information as part of the digital identity, or would a transactional username suffice? The zero-state challenge. Beyond personal identity, many blockchain efforts are designed to create secure, immutable, and immediately auditable provenance records for physical items. However, what happens if the veracity of those items' provenance initially entered into the blockchain comes into question? This is referred to as the zero-state problem, and it is a major issue for blockchain-based provenance records for physical objects that predate the blockchain. Consider land registry systems and the efforts by entire countries to transition to blockchain for land title recording and transfer. Some of the world's population lives on land without having a clear title, which could lead to significant uncertainty in the initial land title data in a blockchain. Additionally, the falsification of land titles is already a problem in some places, so false land title data recorded in an immutable blockchain could exacerbate the effects on disenfranchised owners. Reliance on private keys. In a blockchain, security and control over a digital asset are established with encryption algorithms and public-private key pairs, which include a publicly known address and a private digital key that can unlock the mailbox at that address. The advantage is that individual users do not need to remember passwords or link their personal information, such as email address or telephone numbers, to collections of stored information. However, users do need their private keys to access the system. If there is no way to retrieve a lost private key, the effects could be considerable. Consider a blockchain-based system to record property titles. An individual will need his private digital key to access control over his property and sell it to someone else. What if he loses his private key? Is there any way to reset or retrieve his private key? If not, does that mean he has lost control over his property? If blockchains are hosting control over assets, especially valuable assets, it is important to incorporate a way to retrieve an individual's private key. The limited lifespan of encryption. Blockchain relies heavily on encryption, and encryption has an effective lifespan. As computational techniques and computer outputs continue to evolve at a rapid pace, so too must encryption algorithms stay ahead of the technology to break through encryption. If immutable and distributed information on a blockchain is encrypted with outdated algorithms, that information may become vulnerable to exposure. This can have significant consequences on people's life if the exposure of personal information leaves vulnerable populations open to exploitation. Blockchains built for long-term applications, such as land registries, must also consider the possible effects of quantum computing to amplify this threat through its projected ability to break through any non-quantum proof digital signatures used on blockchains and forge transactions. Environmental impacts. In the absence of a trusted central authority, Bitcoin-based blockchain applications allow entities worldwide to transact safely and securely, yet they consume significant environmental energy. Bitcoin authenticates transactions on its distributed network using a network consensus rule, or a consensus protocol, called proof of work, which uses brute force trial and error methods to guess trillions of possible solutions to a cryptographic possible. The electrical energy consumption required to accomplish this has become an increasing area of concern, in which leveraging blockchain for social good with a proof of work consensus protocol could risk harming the environment. In June of 2015, the electrical consumption estimated for a single Bitcoin transaction was equivalent to the energy used by an average American home for 1.7 days. By December of 2017, the increasing value of Bitcoin had driven so much competition into the space that the electrical consumption for a single Bitcoin transaction had jumped to 8.45 days of average use for an American home. Alternative ways to create consensus on a blockchain are being designed to address the environmental challenge. So, how can we design a blockchain application to meet these ethical challenges? This is where the ethical design framework comes in. The importance of intentional design. In a traditional design and build context of digital technology, there is an opportunity to modify code and to test and fix design flaws even after the technology has launched. For instance, an application can change how to manage an identity by modifying code and releasing a new version. It's not that simple with blockchain. Once built, it is much more complicated to change course, and any information already in a blockchain is immutable and distributed. This drives the need for intentionality in design to identify what attributes need to be prioritized at the expense of others in the design process. Even before deciding whether blockchain is the right technology to use, social impact organizations need to clearly identify the problems they want to address and the associated outcomes they want to achieve, establish the appropriate ethical approach and guiding values, and understand the available technology choices. This is particularly important in blockchain, in which the rules governing the human interactions with the technology are determined from the earliest stages of design and can be exceedingly difficult to change once the technology is implemented. The blockchain ethical design framework is a tool for creating an intentional design that incorporates key ethical questions for the development and use of blockchain. The overarching goals of the framework are to 1. Give decision makers an outcome-focused and user-centric tool to assess the context-specific consequences and ethical implications of their blockchain design choices. And 2. To enable them to use this understanding to make the appropriate values-based design choices to achieve better social outcomes. For the purposes of this framework, decision maker is considered to be anyone who is influencing a social impact solution that may involve the design and implementation of a blockchain. Furthermore, the framework should be used in a collaborative way that actively involves all of the critical stakeholders throughout the process, from problem definition through execution. The stakeholders will come from a diverse range of communities, fields, and organizations that are involved in all aspects of the relevant ecosystem. Ultimately, these ethical considerations traced broadly to 6 root issues: governance, identity, access, verification and authentication, ownership of data, and security. Together, these factors create the foundations for the development of the framework. The blockchain ethical design framework has 3 phases, each consisting of multiple steps. The first step is defining the approach to creating social impact, and it involves the initial work of understanding the desired outcome and explicitly defining an approach with which to achieve this outcome. The second phase is the design and implementation of the blockchain through a decision spiral approach that reveals the impacts of design choices on the desired outcome and on the people affected by the design. The final phase of the framework is the maintenance stage, in which the steps from the first 2 phases are periodically revisited throughout the life cycle of a blockchain project to ensure the technology is still achieving its desired impact. The first phase of the blockchain ethical design framework is to design the approach to creating social impact. From the beginning of the first phase, critical stakeholders need to be involved in a collaborative process to maximize the robustness of the overall impact. These stakeholders will come from a diverse range of communities, fields, and organizations that are involved in all aspects of the relevant ecosystem. At the beginning of a blockchain design, it is critical to explicitly identify the desired social good outcome of the project in order to provide clear direction throughout the design process. Furthermore, there are many different types of ethical approaches that could be prioritized above all others while designing a blockchain to achieve the desired outcome. For instance, prioritizing the minimization of harm to participants is a very different ethical goal from maximizing participation, which in turn is very different from ensuring equitable access to a service. To achieve a desired outcome in accordance with the designated ethical approach, it is important to develop a design philosophy that will guide all of the specific design decisions. This design philosophy is a set of guiding principles that are informed by both the chosen ethical approach and the assessment of the ecosystem. For example, if the ethical approach is to provide equitable access to financial services across a community, and the assessment reveals significant power and access disparities in that community, the design philosophy could be that every design decision needs to work to minimize the access disparities in the community. After assessing the ecosystem, a design maker may conclude that an alternate data ledger technology would be more appropriate for the context, or that blockchain is not an appropriate technology because an immutable record would be harmful in the given context. A decision maker should proceed with the framework at this point only if blockchain is still seen as a viable technology option for the desired outcome. This phase involves the initial work of understanding the desired outcome and explicitly defining an approach with which to achieve this goal through a series of 5 discrete process steps. First, define the problem being addressed and the desired outcomes. Second, explicitly identify the ethical approach. Third, assess the ecosystem of the desired outcome. Fourth, determine the guiding design philosophy. And 5, determine if blockchain is an appropriate technology choice. Therefore, the framework begins with identifying the desired outcome of the project to ensure that it benefits the end user in a meaningful way. Using this desired outcome as the guiding principle, the framework explains how to conduct an initial assessment of the project's ecosystem. This ecosystem assessment is important to understanding the full context of the desired outcome and how the elements of that context interact to affect the outcome. The results of the ecosystem assessment will then be used in conjunction with the appropriate ethical approach to determine the guiding design principles of the project. These principles will serve as the ethical backbone of the project. They will provide the standards to which the project will be held and against which the design choices will be measured. However, before moving on to the design spiral, it is important to reevaluate and decide if blockchain is an appropriate technology choice for the project. If blockchain is determined to be an appropriate technology choice, users will enter the second phase of the framework represented by the design spiral, which addresses blockchain-specific questions. To elaborate, Step 1. Define the problems and the desired outcomes. The framework is guided by an outcome and user-focused approach to driving social impact. Blockchain technology holds immense potential for social impact applications, but it's still just a technology. Ultimately, the decision makers behind the technology are responsible for delivering an outcome that benefits the end users of the technology. By making the outcome and the user central to the design process, the framework holds decision makers accountable for their goals and to the users. The first step of the framework is to clearly define the problem, including addressing any inherent bias, identify the desired outcome to solve that problem, and create a system that supports the realization of that result. This means ensuring that every aspect of the design, including the choice of technology, is in the interest of reaching the outcome. However, it is also essential that the outcome be evaluated through the user's perspective and address user needs through the lens of an ethical approach. Step 2. Identify the ethical approach. Making ethical design decisions involves identifying an appropriate ethical approach and understanding the resulting principles and values that underpin a project. Ethical design and decision-making can follow many possible ethical paradigms and approaches. The approach could focus on maximizing the benefit for and minimizing harm to the users. A different path might prioritize the overall social benefits of the blockchain project, even if that creates the risk of harm to some individual users. One ethical approach could be to create a system that treats all users equally, while another could focus on ensuring the welfare of all users by tailoring the system to function differently for individual segments of the user population. Each of these represents a valid yet slightly different ethical approach, and in practice, a combination of these approaches will generally be used. The lecture 4.4, Technology Assessment, can help to define an ethical appealing scenario for further decisions. Step 3. Assess the ecosystem. Conducting a contextual or ecosystem assessment for the desired outcome is critical since outcomes do not exist in a vacuum. Rather, they are driven by an ecosystem of factors: the user, community, existing infrastructure, financing, and technology options. Therefore, the third step of the framework is to conduct an ecosystem assessment to thoroughly understand and acknowledge the roles that each of these core components plays in contributing to an outcome. The roles of these components are often connected via a web of complex interactions, and these roles may vary throughout the project timeline. Knowing the context for an outcome is the only way to effectively achieve the desired outcome. Using the desired outcome and the chosen ethical approach as inputs, the ecosystem assessment will guide the development of a project's principles and values, provide an understanding of how the goals of the project map to the ecosystem components, inform the answers to key design questions, and act as a framework to evaluate the design decisions within. However, ecosystems are not static. They are fluid and will continue to change and evolve throughout the life cycle of the project. It is particularly important to understand not only natural changes to the ecosystem, but also how the design and implementation of a blockchain solution may hasten or spur these processes. However, just as the assessment should be periodically revisited to inform and evaluate key design choices, it should also be updated and reconsidered as the project progresses. To better assess the ecosystem, we offer different methods in Lecture 8.1. Step 4. Determine the design philosophy. The fourth step of the framework is to determine the project design philosophy by defining the values and guiding principles underpinning a project. The design philosophy could include ideals such as equity, fairness, transparency, the right to individual privacy, and the right to own property. Whereas the ethical approach provides a framework for considering how standards are set, the values outline the project's priorities. For example, protecting user privacy would be an important guiding principle that aligns with the ethical approach of minimizing harm to users. In digital identity use cases, no sensitive private information would be put on the blockchain directly. The blockchain could link to the information, or the blockchain could use zero-knowledge proofs in which there is a verification on the blockchain of the existence of an identifier such as a social security number, but the social security itself is not on the blockchain. This is one example of how the ethical approach and values are considered together to constitute the design philosophy. The guiding principles and values are determined as a result of assessing the ecosystem of the desired outcome within the context of the chosen ethical approach. By understanding how the ecosystem components interact to create an outcome and the resulting ethical implications, a decision maker can identify the guiding principles and values that will have a contextual impact and create the foundation of the entire design process. This will help the implementer navigate inevitable design and implementation trade-offs, especially when values and guiding principles are in conflict. For example, there may be a conflict between equity and fairness in a blockchain that provides user access to services in a context with severe inequalities. Valuing equity in outcome in this example may lead to optimizing the blockchain to provide priority access for the most vulnerable users, while prioritizing fairness in the design philosophy may result in a blockchain that provides all users equal access. The design philosophy is important because it creates a sound foundation for the entire design process. Step 5. Determine if blockchain is an appropriate technology. Blockchain is not always the best option for achieving a desired social or environmental outcome, so the fifth step of the framework is to decide whether blockchain is a viable technology option. Once a desired outcome and an ethical approach has been determined, an ecosystem assessment has been conducted, and a design philosophy has been defined, a decision maker must determine whether blockchain is a viable and appropriate technology option. To decide whether blockchain is the right technology for the respective use case, we refer to Lecture 4.2. Here, different decision paths are listed. Phase 2. Designing and implementing the blockchain. Research and conversations with expert stakeholders have identified hundreds of questions related to different ethical concerns in blockchain applications. To better understand and structure these questions, 6 root issues for ethical considerations were determined: governance, identity, verification and authentication, access, data ownership, and security. These areas span the breadth of questions and concerns raised. Though there is some overlap and the categories are not entirely distinct, we have found them to be a useful taxonomy for delving into design. These are defined by 6 overarching questions. How is governance created and maintained? How is identity defined and established? How are inputs verified and transactions authenticated? How is access defined, granted, and executed? How is ownership of data defined, granted, and executed? How is security set up and ensured? Governance. Governance refers to the establishment and maintenance of the rules that govern the entire blockchain system. A fundamental characteristic of blockchain technology is having a rigid set of rules by which all transactions within the system are governed. In the social sector, it is critical to ensure that a sound human governance structure is driving the technology. Here is an overview of questions that are asked to reflect the ethical issues in regard of governance of blockchain. Key design considerations include determining who the stakeholders are, their roles, and how their roles are established. Establishing the processes, rules, and regulations of governance, both technical and otherwise. Creating pathways for these rules and roles to change over time. Having a plan for closing out or continuing the system if key stakeholders leave. Key assessments considerations include the stakeholders who need to be included to bring about the solution, the roles and relationships of stakeholders, the ways in which the technology may formalize currently informal processes, and how changes in governance and governing processes will affect users. Identity. Significant ethical considerations surround what constitutes identity and to whom identity is granted in a given blockchain, and how identity information is used, accessed, and protected. Multiple pieces of identifying information collectively create a digital identity. Blockchains can be used to establish limited or transactional digital identities for accessing information or services. Blockchain systems can also be used to establish portable, foundational digital identities. In other words, identities that are permanently linked to a unique individual and can be used in a variety of contexts, moving with the individual to prove identity or credentials. Key design considerations include understanding who is granted identity in this context, understanding the level of identity required for the solution, determining which identifiers will be used to constitute this identity, and preventing exposure of personally identifiable information on a blockchain. Key assessment considerations include understanding which identifiers are available and formally accepted within the community, and understanding which identifiers put users or the community at risk. Verification and authentication. How inputs are verified and then authenticated is critical in an open ledger system. Verification of information put onto a blockchain presents a range of challenges. For digital assets such as cryptocurrencies or digital photographs, the verification process is closely related to the transaction authentication process to determine if the entity initiating a transaction has control over that asset. When linking a non-digital asset, such as a person or an object, to a blockchain, verification becomes more complicated because it introduces human interaction and, therefore, various political, legal, and ethical obstacles. For instance, how can someone's claim of land ownership be verified? Key design considerations include determining how and by whom verification will be done for in the initial entry, follow-on data input, and how transactions between users are authenticating, ensuring that the established process can be trusted by all stakeholders, and understanding any social impact of consensus protocol algorithms. Key assessment considerations include understanding current barriers, including disputes over information, and knowing who currently verifies/authenticates information, the processes, and the potential issues surrounding these. Access. The definition, granting, and execution of access are critical to any person's ability to use and interact with the blockchain system. Also, the scope of access to individuals' personal information on a blockchain may result in serious implications for those individuals if that information is exploited. Beyond the specifics of accessing a blockchain to view or write to the ledger, access also includes more intangible questions around digital literacy and the effective ability to access the system. Key design considerations include who has written permissions, who has read permissions, how these permissions are established, and the level of access that users are granted. Key assessment considerations include understanding which stakeholders currently have access to information, which needed to execute the service, and which would benefit from having it. Users' familiarity with and access to different digital technologies, financial incentives for certain groups to have or to not have access, and understanding if there are conflicts of interest in who might have access to the data. Data ownership. There are important questions about who owns the data, who exercises control over the data, where and how the data is stored, and how adjustments are made to incorrect information. A compelling characteristic of blockchain is its ability to give users the power to exercise functional control over data. For example, the Sovereign Foundation is building a self-sovereign identity trust framework that creates a robust governance structures that allows, among other things, people to exert positive control over their personal digital identity information. Key design considerations include determining who owns data, both in name and in practice, understanding how stakeholders can use and benefit from owning the data, deciding if data will be stored on the blockchain or externally, and creating a process for users to flag and fix incorrect information. Key assessment considerations include understanding how data is currently being stored and whether that repository could be leveraged, identifying who currently owns data and how they are able to use it, and understanding if users would benefit from having ownership of their own data and what data ownership would effectively mean. Security. Data can be scattered throughout this distributed infrastructure, thus reducing the vulnerabilities compared with data that is aggregated and stored in one location. Individual users do not need to remember passwords or link their personal information, such as email addresses or telephone numbers, to collections of stored information. However, there are ethical challenges here as well. Blockchain security uses encryption algorithms and the use of public/private key pairs that are like publicly known addresses and a private digital key to essentially unlock the mailbox at that address. Blockchain technologies have been increasingly used to secure private information, such as health records. What would happen if someone lost her digital key to control her assets or medical information? Key design considerations include determining who establishes security as well as who is responsible for breaches of it, ensuring that vulnerable data is adequately protected against current and future threats, deciding how different pieces of information will be protected, and creating a system for safe and effective access to private keys. Key assessment considerations include knowing users' understanding of potential cyber threats as well as their capacity to protect themselves from them, and being aware of what security threats the community faces and how they may change over time. The initial assessment and design process accomplished in Phase 2 of the framework sets the stage for creating positive social impact with blockchain technology. However, context changes over time. The choices made in the initial implementation of blockchain technology may lose relevance or create unintended consequences for people as the context changes. Therefore, the framework is iterative by nature. Phase 3 of the framework includes periodically revisiting the earlier phases across the life cycle of a project. A notional project life cycle is shown in the diagram. It starts with an iterative assessment and technology design process, then moves into technology development and deployment. After technology has been deployed, it will be sustained until it reaches an end of its life cycle, where it is either transitioned to a new technology or redesigned. Thus far, the framework has focused on the iterative design spiral in the initial project design phase, but it is critical that the design philosophy to be maintained and implemented throughout the project. In phase 1, decision makers answered the 5 entry questions. In phase 2, they worked iteratively through the design spiral multiple times to fully understand the complex interrelationships among the various assessment elements and design choices. After development and deployment of the project, the first 2 phases should be periodically revisited and evaluated at key review points throughout the project life. This maintenance pattern is necessary to account for the evolution of the desired outcome, the ecosystem, and the technology throughout the project. This repeated, rigorous evaluation ensures that ethical considerations are taken into account and that the project aligns with its design philosophy throughout the design, development, deployment, implementation, sustainment, and evolution of the project. Conclusions for social impact organizations and policymakers. The promise of blockchain to have an impact on millions of people is real. Its key attributes of transparency, trust, and immutability have the potential to improve lives across the globe. By increasing efficiency, security, and verifiability in the way that social impact organizations operate, access to services is delivered, data is stored and controlled, and assets are tracked, blockchain's potential can literally change the world. However, the realization of this potential to improve lives requires an ethical approach that recognizes the relationship between design and human outcome. As blockchain solutions are built and deployed, the blockchain ethical design framework provides a way to ensure that social value is protected. It is a tool for practitioners to drive ethical intentionality into the design of blockchain technology. Thank you for watching this lecture, and I hope to see you in the next lecture of this module.